Hey there, folks. It should be Monday, the 28th of September. And today we are looking at earthquakes. We talked a little bit in the last lecture about volcanoes and said, volcanoes are kind of dramatic and people sort of remember them, and kids like to do science fair projects on volcanoes. Earthquakes are also very dramatic and probably affect more people, as we'll see. Because they're a little bit more widespread. So you may not live near a volcano, but you may have experienced an earthquake. Here in Kentucky, if you've been around a little while, you have experienced a few small earthquakes. You may not have realized it at the time, but you probably did. Um, as we'll see, earthquakes are not uncommon to Kentucky, so it is quite possible that we could have a big earthquake here sometime in the near future, even though we don't live near a plate. And we'll talk a little bit more about that too in also more detail. So let's jump into the chapter here. This is chapter 10. And there's a little story here at the beginning, like they do a lot of times, talking about a particular earthquake. This one happened in 2011 in Japan. Japan gets a lot of earthquakes because they are near a fault zone. They're near a subduction area, and so they do get a lot of earthquakes. We hear a lot about Japan and their earthquakes. Now, that doesn't mean that Japan itself gets a lot of earthquakes. There's earthquakes all around, but because there's so many people living in Japan, we hear about them because so many people get affected. So you can think of an earthquake as sort of like a stick, sort of like breaking a stick. So the Earth's crust is solid, but it sits on top of this liquid layer, this semi-liquid layer called the asthenosphere, as we've learned earlier. And so, being solid, it can crack, it can have joints in it, it can move. And so, similar to a stick, if the pressure gets applied to it, it may not move right away, it begins to bend, but then all of a sudden, the stick sort of gives way and the crust sort of gives way, and there's a big crack and a big break and big movement, and that movement is an earthquake. We call those faults. So where there is movement in the lithosphere, in the crust, we call that a fault. And we'll see these faults are not nice, even lines. They can kind of go all over the place. So there's been lots of famous earthquakes over the years. And again, earthquakes similar to volcanoes have really steered human development and human society, where we build, where we live. Because really, you stop and think about it, it's not the earthquake that kills people, is it? What kills people is the fact that the buildings we're living in, or the bridges we're walking on, or uh, um, collapse, and that's what kills us, kills people. So it's not really the earthquake itself. They've been going on for billions of years. It's the fact that we live on the surface of the planet and we live in structures that are not uh, that aren't capable of withstanding earthquakes. So you might think, well, then what we need to do is start thinking about how we can build buildings that are strong enough, or at least more flexible enough, or different in some way to sustain earthquakes. And you'd be correct. That's exactly what we're trying to do. Here we see a tsunami. We'll talk about those in a little bit more detail. So earthquakes can cause tsunamis, and that one in Japan, I believe. So anyway, what causes earthquakes? We call this seismic activity. Here you can see some of the notable earthquakes. And again, our textbook is kind of old, so we've even had some biggies after 2011 that have caused a lot of damage and affected folks. But this is a result of what we call seismic activity. And here are some lists of some things that could cause this: formation of a new fault, in other words, just a new crack in the plate; sudden slip of an existing fault. We'll talk about that in more detail. A phase change in terms of minerals, kind of rare, but it can happen. Movement of magma, um, a landslide, a meteor impact, or even a nuclear bomb test. And then even today, we're doing a lot of what we call fracking. And so we're noticing lots of earthquakes caused by trying to release natural gas by breaking up the rock. And once that gas is released, then it releases the pressure underground. And so that can cause earthquakes. So some folks who have been around places where they're doing a lot of fracking are seeing a big increase in earthquakes as well. So we call the point where the earthquake happens down in the ground the focus, and then wherever that place is right above it on the surface, we call that the epicenter. Since we live on the surface, we're concerned about the epicenter, where the earthquake under your feet actually starts. So see, these are faults in the crust, and we're not going to get into a lot of detail with these different kinds of faults, strike slip faults, and reverse strike slip faults and thrust faults. We're not going to get into that in too much detail, but please read the section so you kind of understand how these different things can form. So here's an example of some earthquakes, and usually what we see is a strike slip type of fault in an earthquake. So there you can see a fence where at one time the fence was nice and straight, and with the displacement of the fault, we can see that it's not straight anymore. We see this a lot of times in aerial photographs. On the right, you can see a road that sort of stops and then starts somewhere else. And I've even seen pictures of orchards where all the trees were all lined up, and now they're not lined up anymore. So they're caused by friction, and your book goes into some ways of kind of demonstrating this. The best way I have of demonstrating is to take your two hands and put them together, and then kind of push together with some pressure, and then try to slide your hands. What you'll notice, of course, is your hands don't want to slide, but if you increase the pressure, all of a sudden they slide very quickly. And that's a good example of what happens in an earthquake. So the pressure builds up over time. Friction holds the plates together until the pressure is greater than the friction, and then we get a displacement, and we get an earthquake. And again, here's an example of that with a piece of wood. And there you can see how underneath the ground we have these broken off pieces that slip and break. Again, kind of like a spring here. They're showing you that this is kind of like a spring where you pull, and then all of a sudden the pressure is greater than the friction, and the block will slide. When we have earthquakes like this, we have foreshocks and aftershocks. So the foreshock is kind of the biggie, usually. But like a spring, if you let go of a spring, it kind of bounces back. It goes back to where it started, but then it kind of bounces a little bit. And those are kind of like our aftershocks. So once you have a foreshock, once you have the initial earthquake, a lot of times that area, the pressure got released. But what that means then is it adds pressure to other areas. And so those areas that already had some pressure now suddenly have more, and then they can also release pressure. And so you get kind of a chain reaction, and you can have aftershocks that can last for quite some time. Usually, and not always, but usually the aftershocks are not quite as bad as the original earthquake. So anyway, your book here talks about shows you a map here of looking at some faults that have happened in the past and what you might see. So sometimes you see these escarpments of rock, and those could very well be the results of an earthquake. The fault happens usually deep in the earth, but it affects what is on top of the earth, and we'll see that in just a minute when we start talking about the different kinds of waves. Alrighty. So moving through this just a little bit. Again, there's a lot of these earthquakes, so they talk about a lot of these different kinds of earthquakes. Can faults slip without earthquakes? Sometimes. Some of the research that they've been doing, especially with subduction zones, is that in some subduction zones where they would expect to have lots of earthquakes and they don't have a lot of earthquakes, they think it's because of the decrease in friction. In other words, the fact that they're underwater, the fact that the material is not hard rock, but kind of a muddy material, that the plates slide a little more easily, so you wouldn't have as many earthquakes. So there are places where you can have these slips and faults and not have a lot of either earthquakes or even big earthquakes. So let's look at what happens in an earthquake. So when an earthquake happens, what we're feeling is energy. And this energy comes to us in the form of waves. Just like the wave you're hearing right now as you hear my voice, I'm releasing energy. I'm bouncing air molecules off of each other using my vocal cords. Those air molecules are going across the air, bouncing into other molecules. And finally, those molecules are going to bounce into molecules right next to your eardrum, and you'll be able to hear and understand what I'm saying. So seismic waves work in very much the same way, except waves are not moving through air necessarily as they are moving through rock or earth. So we call these seismic waves. We have two different kinds. We have body waves and surface waves. Body waves are the waves that pass through the interior of the earth, and surface waves are waves that travel on top of the surface, on the earth's surface. Body waves are faster. This is kind of weird. When you stop and think about waves and energy, one of the examples I use is thinking about water. Can you hear underwater? If you've ever been in a pool and been underwater, you can hear stuff above the water. You can hear stuff in the water. So because water is more dense, believe it or not, sound actually travels faster and farther in water than it does in the air. There are known cases of whales that can be 100 miles apart and be carrying on a conversation with each other. So the earth is even more compressed than water, so waves travel pretty easily and quickly through the earth, whereas surface waves have a tendency to get more resistance, and so they don't travel quite as much. So in just a little bit, we're going to understand that these waves, these body waves, generally travel faster than surface waves. So in an earthquake, you might actually feel, and if you've ever been in a big earthquake or seen video of a big earthquake, what you see first is kind of the vibration. Well, those are the body waves kind of getting to you first. And then after the vibration, a few seconds later, that's when the surface waves hit. And that's where the lights start swinging and the stuff starts falling off the grocery shelves, and people fall down and buildings fall down. So it's these body waves that hit us first as sort of vibrations and let us know, hey, an earthquake is coming. But then just a few seconds later, and again, we'll see, depending on how far away the epicenter was, you'll get these surface waves, and they're the ones that do a good bit of damage. So the body waves and surface waves, these are compressional waves. So if you think about a slinky, and we'll look at some pictures here in a minute. If you think about a slinky, it's like if you push the slinky back and forth, and you can see the wave kind of inside the slinky as it moves back and forth. The sound waves I'm using right now are compression waves. In other words, the molecules are bumping into each other. The direction of the energy is going in the same direction as the wave, if that makes sense. However, some waves, like the S waves and the R waves, S waves and the surface waves, are shear waves. So now shear waves are kind of like ocean waves, aren't they? The wave moves up and down, but the energy moves back and forth. So in a shear wave, the wave is moving 90 degrees to the movement of the energy. So it's a shear. In other words, it's they're not moving together. One's moving up and down, and the energy is moving across. And we'll see pictures of that. You'll see what I'm talking about. So here's the four different kinds of waves. We have P waves, and again, this is stuff you need to know. P waves. P stands for primary. Primary means first. So these are the first waves you would feel. They're body waves, so they're down in the ground, and they're compression waves. So if you're sitting at a table or sitting somewhere and all of a sudden you sort of feel a vibration, right? Those are the primary waves getting to you. The S waves are also body waves, but now they are shear waves. So they're moving kind of like an ocean wave. And so after the initial vibration, you might get some more actually things moving up and down, or things feeling like they're moving side to side. These would be the body waves, these S waves getting to you next. And letting you know that, yes, an earthquake is on its way. The other two, the love waves, L waves, and R waves, are for Rayleigh, these are surface waves. So these are waves that move along the surface. And they're going to be the last waves that come, and they're the most damaging to buildings and to bridges and whatever else. This is the things that kill people, are these surface waves, because they can the L waves ripple back and forth, cause you to fall down, feel like you're drunk, and then the R waves move up and down. And literally, there's some video online, and I'll try to find it and add it to this. Uh, uh, Added to this module, where you can actually see the ground. It almost looks like an ocean. The ground, you can see, look, it has waves in it, and it's rippling up and down, which is just mind-boggling when you stop and think about it. But they do move up and down, called R waves. So here's some illustrations of that. There you see the P waves. There are compression waves. S waves are the shear waves and secondary waves. And again, there you can see the direction of vibration is perpendicular to, and not in the same direction of, the wave energy itself. And then there's the surface waves. Okay. So how do we detect these waves? How do we measure them? We use things called a seismometer. Seismometer is simply a machine that part of the machine vibrates with the wave, the other part of the machine stays stationary, and so it can measure the size of the wave by how far the needle moves back and forth. These are some old-fashioned machines. Today, they're done with computers and accelerometers and all kinds of electronic stuff. So these are kind of old-fashioned looking pictures, but the principle is basically the same, using these instruments to measure the waves. Now, how do we find the epicenter? In other words, if there's an earthquake, how do we find out where the epicenter is? Well, you can take one of these seismometers and you can measure the two waves. You can measure, or at least how far away it is. You can measure it by the difference in time between the P waves and the S waves, right? So the P waves are the primary waves. They're going to get to you first. The S waves are moving slower, so they're going to get to you later. So the farther apart those two waves are, then the farther away is the epicenter. Your book says, think about two cars. One of them is going 50 miles an hour and one of them is going 30 miles an hour. Well, if the two cars pass you and they're fairly close together, then they started out just a little ways down the road. But if the two cars pass and there's quite a bit of time between them, then the faster car has been going for quite a while and has gotten quite a bit of distance on the slower car, and so therefore they started a long way away. So that's kind of how we can figure the distance of the epicenter. Now, how do we figure out where the epicenter is? This is what's kind of interesting. So you'll need more than one station. You'll need more than one seismometer. And we use something called triangulation. Triangulation is used in all kinds of fields of geography. It's used for your GPS, for locating you with using your GPS. It's a kind of a triangulation. So let's think about it this way. Look at the map there on the page, and think about Station 1. So Station 1 has determined that the earthquake happened 2,000 kilometers away from Station 1. Well, we don't know what direction, do we? We just simply know that it's 2,000 kilometers away. So if you took a compass and drew a circle 2,000 kilometers away, then the earthquake happened somewhere, right, on that circle. We don't know where yet, but somewhere on that circle. Well, if we had a second station, right, Station 2, and Station 2 located where it is, says it's 4,000 away, and we do the same thing with the compass, we see where the two circles intersect. So suddenly, where those two circles intersect in two places, it could be up to the north, up in Canada, or it could be the epicenter down in the United States. So we need a third station to kind of seal the fate for us. And that third station would show us that, in fact, the epicenter is in the United States, not the one where the two circles met in Canada. So that's kind of how it's done. It's usually done with more than just three, but this is a good example of how you could locate an earthquake. What about the size? Well, for a long time we've heard that an earthquake is so many, 3.1 on the Richter scale. Richter scale was used for many, many years. It's kind of fallen out of fashion a little bit, and most of the time today we use what's called the modified Mercalli scale, which is very similar to that in measuring intensity. Now, there's other kinds of scales, and so scientists use all different kinds of scales. For example, this modified Mercalli scale sort of looks at damage to measure earthquakes. There's also there you see the Richter scale, and when we talk about magnitude, we use the moment magnitude scale, so we can actually measure the energy released by an earthquake using the moment magnitude scale. Now, the interesting thing about these scales and all these scales are the fact that when we hear about a 5.0 earthquake or a 7.0 earthquake, the numbers seem close together, and it doesn't seem like there would be too much difference between a 5.0 and a 7.0 earthquake. But understand that these are exponential numbers. In other words, a 5.0 earthquake is not 1 times bigger than a 4.0 earthquake. It's 10 times bigger. A 7.0 earthquake is 10 times bigger, or excuse me, 100 times bigger than a 5.0. So this scale is an exponential scale. It's not just a scale of numbers, but we're talking about here they talk about this logarithmic meaning, a tenfold increase in momentum. So please understand that the difference between even a 7.1 and a 7.5 can be almost twice as big, and that's pretty amazing. So the points on the scale mean a lot, because even just 1 point, 7.1 or a 7.2, can be a big difference in earthquakes. And again, we're just measuring energy that's being released, and so we can certainly measure that energy. Now, where do earthquakes occur? Well, we know of some famous ones, don't we? We know that, as we've already talked about, there's lots of earthquakes in places like Japan. We know there's a lot of earthquakes in places like California. And again, because these are located near plate boundaries. And so those are usually where we get some of the more intense earthquakes. And here, of course, is our map locating all the earthquakes over a particular period of time. And you can almost see the plate boundaries outlined by the locations of earthquakes. But as you can also see, some of these earthquakes happen in the middle of plates, and those are kind of the interesting ones. So a lot of earthquakes around plate boundaries, because these plates are moving, crashing together, grinding against each other, and so we would expect to get quite a bit of activity around plates themselves, wouldn't we? Here's some famous ones. Again, California is famous because it's got two plates kind of rubbing together. Part of California, which includes Los Angeles, is actually moving north and west, whereas the rest of California is moving south and east. So it is true that one of these days, part of California will be a big island. It's going to be a few thousand years, but you might go ahead and buy some property there, and it'll be beachfront property in just a few thousand years. That's, of course, the San Andreas Fault. The famous San Francisco earthquake in 1906 was a big deal. And again, Kobe, Japan was a big earthquake, and those 4 folks have lots of earthquakes. Here we can see Japan, see where some of these earthquakes happen. And again, this is caused by the subduction zones, but we can also get earthquakes from rifting and collisions. So continental rifts, these places where the plates are moving apart, right, can also create earthquakes. And collision zone, places where the continents are pushing together and causing mountains to be built, mountains to go up. Those can also cause quite a bit of earthquakes. So here we see this rift area in Japan, lots of earthquakes. And here we see one of those zones where plates are crashing into each other. These, of course, are the Himalaya mountains, the tallest mountains on the earth, and lots of earthquakes there. The problem, of course, with mountains and earthquakes is you get avalanches. And I think a couple of years ago, folks climbing the mountains there, a lot of people were killed by a big avalanche that hit there. What about interplate earthquakes? So we live in Kentucky, and Kentucky is not near a plate boundary. So are we not going to see any earthquakes? Well, that's not true. Actually, one of the most dangerous faults, and your book talks about it here, was the New Madrid Fault, which is just at the Mississippi River. caused one of the greatest earthquakes in the United States back in 1811, 1812. It was so big that apparently it rang church bells in Boston, which is pretty amazing. And it made the Mississippi River flow backwards. As a matter of fact, it made the Mississippi River change course in that now there's a place in Kentucky that you can't get to from Kentucky. So next time you see a Kentucky map, look down in the bottom left corner of Kentucky. You'll see a little piece of Kentucky that's on the other side of the Mississippi River because the river changed course during this earthquake. The interesting thing is this thing hasn't gone off like that before. If it had this time, where there's lots of people living here, it would have caused a lot of damage. In 1811, there weren't a lot of people living out here, and so it didn't cause as much damage. And here you can see that fault in New Madrid, near New Madrid, Missouri, in parts of Kentucky, Tennessee, Arkansas, and Missouri. But if it happened again today, which it certainly could and probably will, it could cause quite a bit of damage. So there are interplate earthquakes caused by, it could be a leftover fault from millions of years ago. It could be a release of pressure somewhere else. It's hard to tell what causes these kinds of interplate faults. Lots of different reasons. So again, we talked about the fact that earthquakes really don't kill people. It's the buildings and the things that we drive on, like elevated highways and things, that can cause lots of damage. So landslides are another part of earthquakes. Something called liquefaction. So this is kind of interesting. If you've ever been to the beach and kind of played with some sand that had a lot of water in it, if you just let it alone, the sand kind of looks like sand. But if you took that sand with water in it and kind of start vibrating it, suddenly the water comes to the surface. And this is called liquefaction. And this happens a lot of times in earthquakes where the land literally just becomes soup. And buildings that were on nice solid land suddenly are in soup and they start falling over like dominoes. So again, we need to figure out ways of making buildings safer, highways safer, because we're all going to have to live in earthquake zones. So we talked about tsunamis, and tsunamis have kind of been in the news in the last few years. We've had a couple big ones, one in Japan, one in the Micronesia and the Philippines a few years before that. They are big waves, but they're not just big waves. They're actually large amounts of water that have been displaced by an earthquake, which means what happened is, I think there's a good picture here in your book. Here we go. You can see where a subduction has happened, and so the plate that's going under the other plate sort of grabs the first plate, and there sort of drags it down with it, but then at some point it releases its energy and displaces a large amount of water. When it displaces that water goes up and then creates a large wave called a tsunami. So it's not like an ocean wave. An ocean wave kind of comes in and it's gone. This is a large amount of water that just happens to have a wave front in front of it, and they move incredibly fast. Out in the ocean, they can move several hundred miles an hour. The problem is, of course, when they get to near land. I think you got a picture here. There we go. When they get near land, all that water, suddenly the water is getting shallower and shallower, so the water in the front starts to slow down. But the water in the back of the wave is still going 100 miles an hour. And so the whole thing kind of starts, stacking up like a Laurel and Hardy movie where the guy in front stops and everybody bangs into the back of him. And that's kind of what happens in a tsunami. The wave just gets bigger and bigger and bigger until finally it hits the beach, and it's, can be 10, 20, 30, 40, 50 meters tall. So these can be pretty dangerous waves. And they've killed lots of people in the past. Here's some stories about these so you can see that. And of course, there's lots and lots of video on TV or on YouTube. There you can see one of the tsunamis coming in. Now, all those people in the water in that top right-hand picture, all these people are dead. You don't survive a 40, 50-foot wave standing out in the water. So that's what makes them so scary. Here you can see a wave actually coming through the trees. These people probably did not survive as well. So they're pretty scary things. And like I said, if you know what you're looking for, you can kind of be aware of what can happen. So here we've looked at some famous earthquakes that have happened over time, and go ahead and read that. The big thing, of course, about earthquakes is, can we predict them? We can predict the weather now pretty well. We can predict other things, but like we said, with volcanoes and earthquakes, they're very difficult to predict. With volcanoes, of course, we see some evidence, and we can do some predicting in terms of, well, it's going to happen in a couple weeks or a month. With earthquakes, unfortunately, there's almost nothing. A big one can happen in, right now, and none of us would know anything about it until it was over. So we're working hard as scientists to figure out, how we can predict earthquakes. What are some things we can look for? Some things that can warn us that an earthquake is coming. Obviously, if you live in a seismic zone, seismic area, you're going to probably experience an earthquake, and you would probably want to be prepared. But even people like us who live in the middle of a seismic area, we are not immune from earthquakes. We can have earthquakes. There's that New Madrid fault. As you can see, it's pretty big, so it could cause quite a bit of damage if we didn't know it was coming. So again, engineering, making buildings safer, making roads safer, making places that we live in, and with all the people, that's going to save lives. But as far as being able to stop earthquakes or predict earthquakes, that's going to be more difficult. So go ahead and read that section there. And we're at the end of the chapter. And here are our review questions. So if you're going to do these questions, they're here on start on page 357. Do 5 of those and turn those in. And I will see you next time.